6. A 50 millihenry inductor. It's connected in parallel with a 6 ohm resistor. And that whole network, parallel combinations connected in series with a further resistance of 12 ohms and subject to a step input voltage of 96 volts. Yeah. How do we think this one might behave over time? Think about applying the 96 volts. Is it going to start at 0? At the instant we switch on, we've got 96 volts across those two resistors in series. So we're going to get some current flow through there straight away. 96 over 18. Yeah? Agreed? Everyone listening? This will really help. At switch on, got 96 volts across that resistor and that resistor in series. So we've got 96 over 18 is 5 1/3. So we're going to start off at 5 1/3 amps the instant you turn on. Don't think so, I might have. Is that yours? Sorry. Sorry, Jack. Yeah. And then, initially, this is going to present a high impedance because of the back EMF. But eventually, once everything's settled, what will be the resistance of that inductor? Just a piece of wire. We haven't given it a resistance that's so low that we've ignored it. So that's going to act like a short circuit. We're going to have therefore this will be ignored and we'll have 96 volts over 12 ohms. So we'll get an exponential rise up to 8 amps. That's what we're expecting. Yeah? It's worthwhile being able to think about it like that. Why amps? Why 8? Because once the transient period is over, Ben, that inductor is acting like a short circuit. Yeah? If we'd have given you a resistance, then you'd have a parallel resistance in series. Again, if that was 1 ohm, then once that's settled to DC condition, you've got 1 ohm in parallel with a 6 ohm, so that whole bit would be less than an ohm. You'd have 96 volts over, let's say, 12.5. Yeah, so you're going to get an exponential rise as the inductive action of that fades away over time. Yeah? All right? So, but we're going to use our Laplace transform techniques to prove that. Yeah. So, the expression for impedance in the S domain is plus we need to be able to write it as one single expression. So that's using the product, multiply the two together, divided by the sum. Product over sum rule for two impedances in parallel. Yeah. And Vs is simply 96 over S. In this instance, okay, it's easier. I'm going to move that up there because in this particular instance, we can divide through by 0.05 here and get S on its own in this part of the expression. So divide by, and we're talking about dividing just that bit. By 0.05. So we end up with ZS is 12 plus, if we divide that through by 0.05, we end up with 6S on the top. $120 there, plus S. And that just tidies that up a little bit before we start to bring in the next bit, bring the voltage in. The other thing we want to do is write the whole thing as a single fraction. So we need to write as a single fraction. All right. In other words, we want that and that to have the same denominator. What's the denominator on here at the moment? 1. Yeah? So if we multiply by we're effectively multiplying by what? Yeah. So we aren't changing anything. If we multiply that by that, we've still got the same thing because we've effectively just multiplied it by 1. Yeah. So that means that we can write ZS is equal to 12 times 120 plus S over 120 plus S plus 6S over 120 plus S. And therefore now, because they have the same denominator, we can write it with one denominator. ZS is equal to 12 120 plus s all over. And this is plus 6s. If we multiply the brackets out, we get 1440 plus 18x all over 120. So that's our expression, impedance. Therefore, IS is equal to VS, which is 96 over S, divided by all of that, 1440, 18S over 120 plus S. And then we turn the bottom fraction upside down. And multiply. What there? Yeah. I've just done that to save a bit of board space. Right? So now what do we do with that? What does that look like that you've seen before, denominator wise? Yeah? And because we've got we're expecting that kind of behaviour, going to be a partial fraction element to this map. Yep. So we could write that as partial fractions. We can say that 96 120 plus S over S 1440 plus 18S is equivalent to I over S plus B over 1440 plus 18S. Yeah. Which is equivalent to I times 1440 plus 18S plus D times S all over the common denominator S 1440 plus 18S. Yep. Next step in partial fractions? Andrew is? I asked you because you weren't here earlier. Doesn't matter, I just asked if you can remember. Remember equating numerators? Because the two denominators are equal, we can say, because that and that are equal, they are exactly the same, then if that's the case, then that top numerator there and that numerator must be equal. So we can say 96 120 plus S is equal to I 1440 plus 18S plus BS. Yep. And then we can let S equal 0. Therefore, 96 times 120 is equal to 1440 times A, because that 18 times S is nothing. Okay. I is equal to 11520 over 1440. I got that equal to 8. Yep. Just check it in case I made a mistake. You got that, Dom, did you? Right. So I is 8, and then we say let 1440 plus 18S equals 0. (18S) is minus 1440. S equals minus 1440 over 18 minus 80. And then we can put I and B back into partial fraction. What? Yeah. Oh no, we got S. Sorry. We've got to get B. False part then. Take. So we can now go. Therefore, 96 times 120 minus 80 is equal to minus 80B. No, because you've got rid of A by saying that that is equal to 0, the bit in the brackets here, then A times 0 is 0. So that's why you do that. You make initially S equal to 0 to get rid of the B term, don't you? And that allows you to calculate what A is. And then you let that bracketed term equal 0 find out what S is and apply it to that side to find B. Yeah? B equals 3840 over minus 80. A and B in a partial fraction. So we have IS is equal to 8 over S minus 48 over 1440 What do we need to do now? Sorry? Yeah, you need to take that bit on its own and divide by 80. So we get IS is equal to 8 over S minus 48 over 18 is 2 2/3 over 80 plus S. You'll get, have I got it right or not? Yeah? 0.666, 2.66666 if you got your calculator set up like that. Yeah? So we know what that is in the time domain, and we've got that looks like a constant over S. This looks like a constant over another constant plus S. So we've got two expressions there that look like something in the table. We can now write our expression for I at time t is equal to 8 minus 2 2/3 e to the minus 80 t amps. Is that where you need it? I'm just going to graph that so we can see that it does look like what we suggested it might look like. So switch on, time is equal to 0. We've got 5 1/3 amps, and after a certain amount of time period, we got close on 8 amps. Remember, in theory, this exponential rise never reaches the limit, but it's tending towards the 8 amps. What from the expression? Because initially the current's going to be initially this bit, the exponential bit on the end, will be taken off there. Yeah, because that'll be at 2 2/3 at time is equal to 0. Because if you do e to the o as what? Any number to the power of 0 is 1. So you've got, forget that, and you start off with 8, take away 2 2/3, which is 5 1/3. Yeah. So for that circuit, you can't factorise. I said you'd come up against an expression where you can't factorise these two numbers here and here outside the bracket because they're different. One thing to watch for is, with these problems, b always ends up as negative in these partial fraction problems. That's never positive in there. So if you end up with a positive b, you've gone wrong somewhere. All right? What from thinking about the circuit then? Because initially this presents as a very high resistance. Because remember Lenz's law, you've got a very rapidly changing current. It's going whack straight up, right? That's going to induce a voltage in the inductor that is forcing a current back in the other direction. So while the change is rapid, that voltage will be high, and this will present as almost an open circuit. Yeah. So imagine taking that out. You've then got 96 across 12 and 6. 96 over 18 is 5 and a third. That's how we estimated it in the first place. So you're using this. Remember this in a maths lesson. This is electrical principles. So you're using what you know about those circuit components to think what are we expecting to happen here. Yeah. So we've already covered what happens with just an inductor and a resistor in series. We knew that was exponential rise. Now we've added that to a parallel circuit, so we're going to start off with some current, but still get exponential rise to a limit. All right? With an inductor, that's what you're going to see. Yeah. All right? Yeah. If you get that in the exam, you'll not have a resistance to go with that inductor. It will be assumed as negligible like that. It'll be like that. Because if you think that you add a resistor in there, you're adding some more complexity unnecessarily to the maths. All right? No, that 6 ohms will be there, but there won't be a series resistor. Well, I won't give the inductor a resistance. All right? So we're assuming that's negligible enough not to make any difference, Dom. All right? Question 7, is it? Next one. Yeah. Question 7. Determine expression for the current IT during transient period. Sketch a graph that clearly indicates the initial and steady state currents. All right. So we've got a circuit that is 8 ohm resistor in series with a 0.2 farad capacitor. That has got in parallel with it another resistor of 4 ohms, and the whole thing is connected to a step voltage of 80 volts. And we've been asked to determine the expression for the current. Yeah. So let's start off by saying Vs is equal to 80 over S. That's easy, we know how to do that. Zs, how do I do that? times 4, yeah, product. So that's 4 plus 8 plus 1 over. Everyone agree with that? Product over sum for parallel circuit? You could do, but there's no need to. And what can you do? You can add those two together straight off. So you can say that's 4, 8 plus 1 over 0.2s over 12 plus 1 over 0.02s. Yep. And then what? That was tomorrow. Tomorrow afternoon. Tomorrow. That is. Hang on. Multiply the brackets first on the top. Four eights are 4 over 0.2. Hang on, what have I got? What? That should be 0.2. That's part of the first one. Just looking at my afternoon here, and that's not that. Hang on, just let me think about this a minute. Cool. 12 times 0.2 is 2.4s, and that becomes the constant 1. Yep. So now we can write an expression for IS, which is VS 80 divided by S, that is, all divided by that lot. turn the denominator fraction up the other way. What we got to do now? Go on then. Finish that question off. How do you get what, Jake? Right, so using partial fractions, IT 2.4s plus 1 over s times 6.4s plus 4 is equivalent to a over s plus b over 6.4s plus 4. And I learnt a lesson today. Don't ever say something always happens unless you're really sure, because in this case b ends up as positive. Always be careful about saying things like that, Michael. So we can say it's equivalent to I times 6.4s plus 4 plus bs all over the common denominator, s bracket 6.4s plus 4. Equate numerators. IT 2.4s plus 1 is equal to I 6.4s plus 4 times bs. At s equals 0, so that's 80, s being 0 means that bit is just 1, so it's 80 times 1 is equal to 80, is equal to I times 4. I equals 80 over 4 equals 20. So we'll get that far. Yep. Let 6.4s plus 4 equals 0. 6.4s equals minus 4. S equals minus 4 over 6.4 equals minus 0.625. Therefore, 80 times 2.4 times minus 0.625 plus 1 equals minus 0.625 B. This bit equates to minus 40 being equal to minus 0.625B. Therefore, B is equal to minus 40 will be as positive. Yep. I and B back into partial fractions. So we can now write IS is equal to I, which was 20, over S plus B which is 64 over S plus 0.625. Hang on, I'm right. Like that, yeah. 64 over 6.4 S plus 4. And then we need to divide through by 6.4, this bit only. So that remains 20 over S. That is plus 10 over S plus 0.625. Yeah. Transform back. IT is equal to a constant 20 plus 10 e to the minus 0.625 t. Again, there's no common factor there. All right. And this, go back it the other way, this is the function we get. We start off at 30 volts, at 30 amps, sorry, and we fall towards, tending towards 20 amps. Yeah. And if we go back to the circuit, can we explain that behavior at the circuit? At switch on, we will have the whole 80 volts across that 4 ohms. So at switch on, we'd have 80 over 4, it's 20 amps. There's no voltage across the capacitor at switch on, therefore we must have the full 80 volts across there. 10 amps. 10 amps and 20 amps make 30, so we expect it to start at 30 amps. Yeah. When the capacitor is fully charged, what will be the current up here? Yeah, because if all the voltage 80 is across the capacitor, by Kirchhoff's law, none across the resistor, no current flowing. So after the transient period, the only current flow is 20 amps through the 4 ohm resistor. Yeah. So you can kind of, if you understand the underlying principles of capacitor charge, discharge, inductor charging and discharging, you can make an estimated guess as to what the shape of the graph look like and what the results might be before you even start, using underlying principles. Think about what happens at the instant it turns on, under what the expected conditions of the components are, and think what happens after the transient period is finished. A capacitor will be like an open circuit after the transient period, fully charged up, and an inductor will act like a short circuit after the transient period. All right, we'll wrap up there for this week. All right, and I'll go through RLC series circuit next week and some revision on the complex waveforms. Okay.